Today we are going to talk about the last and final advanced integration technique that we really have to worry about, and that's going to be the integration technique of partial fractions. I will start by saying I apologize for not being here and actually doing this live, but my son actually got strep today, and if I wind up randomly talking to somebody, it's probably him who's sitting here playing with Play-Doh while I am trying to do the video. Partial fractions are something that you've seen before. It's the concept of taking a fraction that has a denominator that can be factored and breaking it into, and decomposing this into a sum or difference of those fractions. You can see up here it talks about the process of taking a rational expression and decomposing it into simpler rational expressions that we can add or subtract. And the significance of this is that we can take something where we can't see an integral, or we won't have an antiderivative that exists, and turning it into a lower power so that we can see an integral that we can actually do. So we're going to use partial fractions when the numerator in a rational function is not a multiple of the derivative of the denominator. Specifically, when we're talking about this, what we're stating is that u sub won't work. We should always look to see if u sub works. We should also be looking to see if there's a factor that can actually be factored out, because that would be nice too. But the significance is we're going to factor the denominator, decompose the fraction, and integrate. Again, you'll notice that there is a note there. Fraction has to be bottom heavy. If not, use long division to find the remainder. If this is not bottom heavy, we're actually going to use that other version that we've talked about where we divide the denominator into the numerator, come up with some basic terms, and then get a remainder that's easy to deal with. So, how does this work? Where does this go? We take a look at a problem. We've got the integral of 4x plus 41 over x squared plus 3x minus 10 dx. And our job is to come up with an antiderivative for that. If we take the derivative of if we u sub x squared plus 3x minus 10, which would be the logical u sub, we would get 2x plus 3. And there's no way, even if I factor out a 4 out of this, there's no way we're going to be able to u sub this question. So we are stuck right now. So this is where partial fractions comes into play. So what this looks like is we will, I apologize 1 second here. What we will do is we will look at the denominator and we will see if the denominator can be factored. And so I look at x squared plus 3x minus 10 and we realize that that does factor. So partial factor decomposition says, well, 4x plus 41 over x squared plus 3x minus 10 can be rewritten as 4x plus 41 over the factors of, what is that? That becomes x plus 5, x minus 2. And that can actually be rewritten into sum a over x plus 5 plus sum b over x minus 2. Now, as a quick review for partial fractions, and I'm not going to ever expect you to show this upcoming step, but in a partial fraction, the idea here is that if we were to look at this, and I could simplify this down, what I could show you is that I could rewrite this as sum a times x minus 2 plus sum b times x plus 5 is going to be the same thing as x plus 5 over x minus 2. And if you notice, this term and this term have the same exact denominator. If the denominators are the same, then what that does is it allows me to set a times x minus 2 times b times x plus 5 equal to 4x plus 41, and we can get the following relationship to pan out. And it's this relationship that we are always looking for in the problem. So we want to be able to evaluate a and b, but we have 3 variables. What's nice, though, is that I can actually set x's into 2 specific numbers. For instance, if I could, one of the numbers I can set x equal to is -5. The intention is to turn this term right here into a 0, which when we do that means that all we're going to be left with is a times negative 5 minus 2 is equal to 4 times negative 5 plus 41. Simplifying this becomes negative 7a is equal to negative 20 plus 41 is 21. A must be negative 3. We can do the same thing for b by setting x equal to 2 with the intention of making the a term disappear. When we do that, we get b 2 plus 5 equals 4 times 2 plus 41, or 7b is 49. Therefore, b has to be 7. All of this algebra is done in order to set up a new relationship. Going back to here and rewriting the integral with respect to this, we would say that we would have the integral of negative 3 over x plus 5 plus, oops, I should put a dx plus the integral of 7 over x minus 2 dx. Now, I'm showing you this way because what I will do from here is I'll actually call this negative 3 times the integral of 1 over x plus 5 dx plus 7 times the integral of 1 over x minus 2 dx. So I'm going to usually set those, the a and the b as factors. I just wanted you to see how this would all pan out there. This becomes a simple u substitution down here. The x plus 5 can be u subbed to become negative 3 times the natural log of x plus 5. And that would be plus 7 times the natural log. Again, using a u sub on this term, this becomes x minus 2 plus c. And that would be your final term. Now, if you need to see the u sub, try it out, see if you can figure out what it is. The reason why I didn't show any u sub step is if I do the u sub here, then du will simply be dx, and there will be no strange coefficients or anything that pans out from there. When you did partial fraction decomposition, that's where you had to stop. If you look at this, there used to be a time where they would have asked you to combine all of these logs. The only log rule you need to realize is if you get terms that you could actually, like no powers out here, in terms that when you combine these, they would just become an over problem. So for instance, this could become, if there's no 7 and no 3, this was just a negative and a positive. This could be natural log of x minus 2 over x plus 5. We'll see an example of that. Actually, I believe there's one in your homework where they do that, and you'll get an idea of how to attack that. Okay, moving on to another problem. Integral of 2x minus 5 over x squared plus 3x plus 2. Again, if I u sub this question, I'll get 2x. That's promising. Plus 3, darn it, we're sad. This is terrible. We are going to have to do a partial fraction decomposition. So, this was a lot of extra steps. There's going to be a lot of steps I'm not going to show here. So, when I'm actually doing this problem, I will set up the 2x minus 5 over x squared plus 3x plus 2, and I will set that equal to some a over plus some b over. And in this case, it happens to be x plus 2, x plus 1. If you would have flipped those, it will have absolutely no outcome on the problem itself, so just be aware of that. If I were to have put x plus 1 first and x plus 2 second, nothing would have happened. So we get the factors, and the step that I want to be able to move immediately to is to realize that I'm going to have to take that a times x plus 1 and get one term, plus the b times the x plus 2. And then we would get that when we make the common denominator. And that, when I do all of that, should equal my 2x minus 5. The 2x values I want to set is going to be x equals negative 2. I usually try to cancel the b out first. So when the x is equal to negative 2, negative 2 plus 1 gives me negative a is equal to negative 2 times 2 is negative 4 minus 5 is negative 9. So my a must be 9. set the x equal to -1 to make the a value 0. And we will do -1 plus 2 is 1, so that is b is equal to -2 minus 5 is -7. So your partial fraction step obviously doesn't take a huge amount of space like this one did. Usually we'll simplify that down and do a lot less work as we go through. Once we have that, I'll go ahead and I will set up my integration. So I will call this first term 9 times the integral of 1 over x plus 2 dx, where the a is turned into a 9, and the 9 being a constant can be factored out. The b is -7, so I'm going to put -7 times the integral of 1 over x plus 1 dx. These are both u substitutions. They're u substitutions, and I'm making that abundantly clear because while they don't do anything interesting in this problem, the u subs will eventually become useful. This becomes 9 natural log of x plus 2 minus 7 natural logs of x plus 1 plus c, and we're done. One of the things you'll notice in partial fraction decomposition is, yes, you're supposed to get a whole bunch of natural logs. That is not on accident, that is on purpose. Third and final example then. Wow, we're 11 minutes in and we're doing pretty good. Can't be too upset about that. Not too shabby. So this problem, we're going to set my fraction 5 minus x over 2x squared plus x minus 1 equal to some a over something plus some b over something. What are those somethings? Well, I see. That's a 2x. That's an x. It's going to be plus 1 and minus 1 because that's positive. I want to have a positive 2 and a negative 1. All right. So what do we have? We have a times x plus 1 plus b times 2x minus 1 should be equal to 5 minus x, where we're going to set x at first equal to, it looks like, 1/2. That's what would zero out the b term. So if x is 1/2, then a, we could have 3/2 a is equal to 5 minus 1/2 is 9/2. A must be 3. 9 times 2/3, the 2's would cancel, 9 over 3 would give me 3. We also need to set x equal to, it looks like, -1. That would zero out the a term, leaving us with -2 minus 1. That becomes -3b is equal to 5 plus 1 is 6. B must equal -2. Awesome. So now we take the problem. We start splitting it. So I've got 3 as my a, 1 over 2x minus 1 dx, plus the integral of, not plus, apparently I want that to be a minus, minus 2, 1 over x plus 1. It's okay, buddy. What happened? Oh, it's okay. You can drop the marker. All right. This is where we have to be careful. The last two problems we've done, we've said, oh, there's a u sub, but it doesn't do anything. If I u sub this problem right here, there is an outcome. That's a 2x. So if I take the derivative, I'm looking at that. If u is equal to 2x minus 1, then du is 2dx, which means we're going to have a factor of 1/2. So this becomes 3 over 2, the integral of 1 over u du, minus 2 times the integral of 1 over x plus 1 dx. Again, I'm not worrying about this term because this is a fairly straightforward u sub. If we take the u sub here, this becomes 3 over 2 natural log of u, but we said u is 2x minus 1. This is minus 2 natural logs of x plus 1 plus c. And we would close out the problem. It's not a huge amount. It's a lot of algebra, zeroing things out, understanding common denominators, how the common denominators work, and how we can utilize those to come up with some easier constants. But the beauty of this is that once you get into the integration step here, it really simplifies the problem down a lot. And I don't know about you, but I like when things become simple. So what you have is you have 3 multiple choice questions that you're looking at. You also had those integration problems that you dealt with. I'm currently working on grading your tests, so those will be done by tomorrow. And we will move on from there. Just giving you a heads up, tomorrow we'll be talking about L'Hopital's rule. Really important rule. We've mentioned it before, but we're going to look at it a little bit more in depth and how it will apply later on in the later on Friday when we start looking at something called an improper integration. I hope all is going well. I make sure you have questions both for this and for the integration by parts. I will post the integration by parts answer key that I've worked up on Schoology as well, so if you have time to take a look at that and formulate some specific questions, or maybe just looking at the work will assist you. Let me know what you need, and I will do my best to assist. I hope you all have a good day, folks, and good luck.